for today's attendance is Cohort 313C, and it's mandatory to fill the feedback form, and it's valid till 48 hours. Kindly note the session code. With that, I would like to hand it over to Mr. Thirumalai to begin today's session. And we'll also take a few questions in the interest of time. Thank you.
Hello everyone. So thank you. Thanks for the nice introduction, Lakshita. Right. So thank you so much. Hello everyone. So I hope my screen is visible, right? Someone please confirm me.
Yeah, it's loading.
It's loading still. Okay.
Yeah, it's visible. Yeah.
Cool. So hello everyone. So it's nice to see that there's a lot of people are joining this meeting for quantum. So I hope our 21-day session is going good, very good in QCODE. I hope you are learning every day new things in quantum computing around that field. So today we are just diving into just an introduction about the quantum machine learning, which is part of this cohort. It's like a weekly expert session on different fields. So I will be taking quantum machine learning today. So who am I? So I'm Thirumalai. Currently, I'm working in research team in Center for Development of Advanced Computing at New Delhi. I'm working in predominantly I'm working in quantum computing. So mostly I focus on quantum machine learning. So I have degree in MTech Quantum Technologies from IIT Jodhpur. I also have 4 years of work experience at Amazon. So that's a small introduction about me. I hope most of in the meeting, kind of aware what is machine learning. Anyway, for better understanding, I will just start give a brief, like small introduction or small summary about the machine learning, and I will directly dive deep into quantum and quantum machine learning. We will not be diving very much to technical depth in this meeting, so we will cover basics, at least an overview of QML, and you can feel free to ask your questions here and there. So if question is valid, I can answer those questions while during the meeting itself if I see any. If there are some questions that need to be addressed like a little longer, so that I can take that questions at the end of the session. So if there are any questions that I'm not able to answer, please feel free to reach me. I will answer you later. I can research about that and I'll get back to you. So let's get started into this. So machine learning, as this definition, this is a famous definition. So machine learning is a study of an algorithm which improves the performance of P at task T with experience E, which means that so there is a computer. We will give the computer some data and we will make the computer learn things about the data. So once the computer has learned the data, if we give any new data, the system or the computer has to, or the model, ML model, able to predict what is the new data that is belongs to either which category, or there can be another model which can predict or estimate what is the value of that value or objective or state of the product, state of the new data based on training of the previous data. So that's a small theoretical formal introduction of what is machine learning itself. So why machine learning is needed and when we use machine learning. So there are a lot of problems in real world. We cannot use every machine learning for every problems, but problems like, let's say there is a space and we cannot go there space in person, where we can send our machines, robots. It can automatically learn based on the training data that we give in that earth. And there are different forms of ML models are available for different applications. As you see in the slide, say for example speech recognition, and we can identify the genomics pattern or drug discovery. All those things can be done with ML. I think I don't need to give a lot of applications of ML, as we all aware, since it is a current domain. So having said that, there are predominantly three types of machine learning are there: supervised, unsupervised, and reinforcement learning. So supervised learning is nothing but our dataset has a label. Let's say example the famous apple orange dataset. Along with the dataset for each data cell, we will be having the label as either this dataset is belongs to apple or orange. So then goes to the unsupervised learning, where we don't have any label for a given data set. It is the ML model. It has to it has to categorize or group the label of the particular data. So unsupervised learning is more of the real world application. In real world, we don't have any label for our data. So more research, more works are going on unsupervised learning. So then we move to neural network. So I hope most of us know this perceptron. What is perceptron? MP is nothing but macular split neuron. This perceptron is basically inspired from the human neuron, which has this head and tail. What it does, it receives the input from the previous neuron of electric signals, and it will process and it will send the same information or pass the information back to the next subsequent neuron through its tail. So the neural network or the perceptron is completely inspired from this one only. So here we have a data of x0, x1, x2, and each of have the corresponding weight of w1 and w2 until wn. So we are not diving deep into what are the weights or what are the bias parameters and all. Basically, we have some set of inputs as a data, which is passed with some weight to our function. This function is a perceptron, which has actually a lot of functions. It will enable one of the function and process this input data and give the output as label whether this particular data set is belongs to which category. The one which I said it's here, the apple orange classification. If we give the image, let's say we are giving the image data set of this apple, and this particular ML model will classify this as a class 1, which means y is the label, which gives a 0, which means if it is 0 it's apple, if it is 1 it's orange. So this is the basic analogy or anatomy of the perceptron itself. So here this fng are nothing but the function that we design for different ML models. Next, we come to the multi-layer perceptron, which is a neural network. In previous slide, we just see one perceptron. The MLP multi-layer perceptron is nothing but series of perceptron or network of perceptrons. We will be having one layer of one input layer which gets all the inputs from the data set, and we can have multiple layers of hidden layers which contains a lot of perceptrons, a lot of neural networks which has a different function that activate this input or process the input, and it will give one output layer which is y, which is where we can able to identify what is our label of the particular data. So this particular picture says that we give x as an input, it does some function x on x based on the weight of the perceptron and gives the output of class as y. So the function that I was keep on mentioning, we can have a lot of functions. So the standard and most popular functions are sigmoid, tanu, relu, and log likelihood. You can see this. You can see what are the function methods that we are using inside this perceptron. So anyway, we are not diving into mathematical part of these things. It's just an overview for your understanding of machine learning. So that's it about the summary of the machine learning. I hope until this time you might have learned what is qubit at least. So I hope you know what is this term. Can anybody like chat? I mean, put in the chat what does it means. The one which I'm rounding. I hope you have learned this thing until this time. So anyone?
They can only write questions, so through
Okay.
they're not.
Okay. Cool. Okay.
Continue.
Okay. That's no problem. So this is nothing but yeah, Ket zero. I could see that. So I hope yeah, it's very good actually. So Ket zero and Bra zero, these are the vector representation of the qubit itself. So I just want you to know understand what is this. I think most of you know this is, and this is nothing but the block speed, which is the representation of the qubit itself. Then having we have seen ML now as of now. So what is QML? So QML is an emerging new domain which combines the principle of quantum mechanics and ML, which it just applies the quantum mechanics principle over the machine learning concept. And QML is completely based on the variational quantum eigensolver, which is a purely physics concept. It is came from quantum mechanics. I hope you might have learned that wiki, or if you not, you can learn and after the session also. So QML just utilize the superposition and entanglement of the quantum, which help us to correlate our data set. In most often in real world, we have data sets of data set has a large number of features, and each features will not be correlated that much since we have different different categories of features. we may not able to correlate or we cannot relate these features in classical machine learning. But using this entanglement, we can utilize this dataset better in QML when compared to classical. Also, when you have large number of data set, we may need to transfer the data set into higher dimension and train the data using kernel method. So that thing may be bit complex in classical machine learning, which can be utilized here in quantum space so that we can learn. So QML is nothing less. We have math and stats. We have computer science, which combines we give the machine learning. Then we have the quantum mechanics, which gives this quantum computing combined with computer science, and quantum mechanics, mathematical and computer science, which all together combines and gives us a QML. So if one has to learn or dive deep into QML or research or do something in QML, he or she has to expert all of these fields. Particularly, you have to know a lot of mathematics, so that will help you to understand QML much better. So we will dive. I will just give the over in this slide. I will just give you the overview of the QML itself, how the model looks like. Let's say we have the classical data, and we can encode this classical data set into a quantum state. So we can do this using by some. There are certain types of mapping of classical data into quantum state, which I will discuss in the further slides actually. So generally, these process or mapping is called as a feature map circuit, and these are completely open-ended. I mean, entire QML itself is open-ended, and still it's under the research process. So you can also come up with an efficient encoding system. I will discuss a couple of encoding system and coming slides. So once we map the classical data set into a quantum state, we can pass that quantum state into a PQC, or popularly we call as ansatz, which is a parametric quantum circuits. So I will also discuss what is ansatz in coming slides. So once we pass this quantum state and append with ansatz, we will be having some parameters inside this ansatz. We need to optimize these parameters and give it back to the quantum circuits. If you see, this entire architecture is kind of similar to machine learning itself. So once we have classical data set, we map into quantum state, and this quantum state is appended with ansatz. So in physics term, we will call this feature map or quantum this encoding itself as a problem Hamiltonian, and this quantum circuit or ansatz is called as a known Hamiltonian. So we just combining this problem Hamiltonian, known Hamiltonian, and we are able to train the circuit, and we optimize these parameters until it is converging into best solution. So what I mean the best solution in VQ is basically finding the ground state of this particular quantum state. So we will go into a future map circuit. So before diving into the future map circuit, in QML there are four different broad categories of models that are exist in current industry level. So which is based that we can classify this based on type of data and type of algorithm that we are using. Let's say I have classical data and classical algorithm. We will be using something called as a CC, which is classical data and classical algorithm, which is actually the classical machine learning techniques. So this is a well-known thing that we have seen, and it is well structured and very these things are very good in industry level. Next, what if happen if we have quantum data and we are using classical algorithm? This particular area is very much less explored, since it is very difficult to train our quantum state in classical machine learning, or I could say it is, again, if we have the quantum data, we have to convert that quantum data into classical data, then we have to train using classical models. So there are very less research or very less application in this area. So then we will be discussing the there are other two categories which has the broad application and wide research, which focus wide research. I mean, those areas has been focused in lot in research domains, which is we have a quantum algorithm for classical data. So this CQ, this is the part that currently exists in most of the places, or most of the researchers are exploring in this particular area. We have classical data, and we are using quantum algorithm to train the model. So the other most important part, which is quantum data and quantum algorithm, which is a QQ. This is the actual quantum part, which has data as a quantum and algorithm is as well the quantum. So this is the actual quantum problem. Again, this area is very less focused, or very less research interests or exist in this particular area, since it is very difficult and also it is emerging. But this is the most important model. This CQ is the most used model, and QQ is the most important model, I would say. So there are as I said, there are type of encoding which we have in current industry standards. So but again, this data encoding still an open ended, or it is completely open to research. So you can also come up with or design new efficient encoding system, but there are certain parameters that we can consider while designing these answers or quantum states itself. So I will discuss a couple of encoding system. As I said, when we have classical data, let's say x1, x2, this particular data set will be mapped to a quantum space into this kate x1 or kate x2 with the amplitude of phi. So these are the available, or I would say some standard encoding systems that are exist in book level, I mean theoretical level. So we cannot dive deep into each of this encoding system since we have limited time. But however, I will dive into like 3 to 4 encoding systems. So we first do the basic encoding, which is very standard and very well known, and very basic quantum and simple encoding of all the encoding systems as of I know. So let's say we have data set of 0.1 minus 0.6 and 10. So our objective is to convert this particular data set into a binary. So we have converted into 0.1 into 0.001, or sorry, 0.001. This first decimal will tell us about the sign of the particular data, and the rest of the bit will tell about the data information itself. Now we have some information in binary. Now we have the data into a binary encoded information like 00001. We can directly convert this binary state into a quantum state. So if you could see, for these three information we are using a lot of qubits, which is completely inefficient, which is again costly to use in real hardware. So this basis encoding is of not much of use in real world. 1 minute, sorry. So this basis encoding is of I mean, using this basic encoding is won't be efficient, or it's not recommended to use in current real world application, since it is using many, I mean, large number of qubits, and we are limited with qubit capacity, and there are a lot of other things has to be taken care when you are using when you are scaling qubit to higher things. The other one of the efficient encoding is amplitude encoding. So I hope you might have learned in previous lectures or videos what does this amplitude exactly means. This is nothing but probability of particular state, probability of the state into that state actually. So alpha is a probability of gate 00 being the psi state. So we can encode our data set into this amplitudes, so which again gives a lot of benefits when compared to basis encoding. As you could see, with one qubit we can encode like, sorry, in 2 qubit we can encode like 4 different information. So again, here we are reducing our space complexity into log n. So when you have large number of data set, you can consider this kind of encoding system in your quantum model. And the most important and efficient and current popular encoding system that is incorporated in industries or research domain is angle encoding. So angle encoding is nothing but encoding your data set into a rotational gates, form of the rotational gates. I hope you might have learned what is rotational gates in your lectures. Anyway, I will just give you the brief about this rotational gates. 1 minute, guys. So you have oryx. Let's say you have oryx of theta on particular state psi, which just rotates this quantum state psi in or x direction with this angle theta. So what we are doing, we are encoding our this particular classical data set into a theta, into a parameter theta. So once we encode all this information, we are ready with the problem Hamiltonian. So here I have to come up with one other one efficient data encoding quantum encoding system, which is called as a phase encoding, which is kind of similar to angle encoding, except the fact that once we have all that classical data set, we will standardize or normalize all those data set into 0 to 2 pi. once we have done that, we can efficiently use this particular standardization into a face encoding system. So again, face encoding is also one of the efficient encoding systems that are currently in use. So these are just a basic encoding system that we have as of now. So next we'll move to the quantum neural network itself. We have seen this particular structure or architecture in our machine learning. We have X inputs and we have weights and we have some activation function, which we have the perceptron and we have activation function which gives some output. So the same model, the analogous of the same model in quantum is ansatz. So this ansatz basically means I guess it's a Latin word. Ansatz is a educated guess. So the educated guess here means that you are guessing some values of theta at the initial stages. You can also start your answers with warm starts, which is if you have already trained parameters for efficient training, you can also start with warm start, or also you can go with educated guesses. This design of answers itself is depend on a lot of factors. So when you have when you say type of answers, broadly there are three type of answers. One is problem based answer, and one other is hardware based answers, and other is a standard answer, which is operator efficiency answers. So while designing, there is no proper way of designing this answers itself as of now, since this answers designing of answers itself open ended still now. So however, how to develop this answers means that we have to go from basic states or standard circuits, and we have to modify our rotational gates and entangling gates. And these answers can be it can be standardized based on some of the parameters which is called as expressivity, entangling capability, and trainability of the answers. So expressivity is nothing but how much qubit space that your answers is utilizing, or how much qubits that has been utilized by your quantum gates. So that is expressivity. This is the most important factor one should consider when designing the answers itself. And hardware constraints are like there are you might have known in QuickSkit is a popular quantum language. So where whenever we have some multi-qubit quantum gates or basic single qubit quantum gates, when we are trying to run these quantum gates into a hardware, we have to transmit this quantum gates into a like hardware dependent gates. So these are the constraints that has to be considered while designing the answers itself. And circuit depth is also one of the important factors that has to be considered in any quantum circuit, not just into a quantum neural network. So the circuit depth is primarily depend upon the number of CNOT gates or multi-qubit gates, entanglement gates that you are utilizing. So one always tries to reduce the circuit depth to increase the fidelity of the circuit. Once we have a high fidelity of the circuit, we can expect very less error rates and more efficiency in the circuit. And I have described discussed about the expressivity already. Entangling capability is nothing but how good your qubits are entangled. Again, these are two depth and technical, and it need particular separate session for this thing itself. And I have also discussed about the warm start of parameters. Warm start of parameters is nothing but once you have one, if you have a model which is already trained, you can extract the parameters of that particular answers, and you can use those trained parameters again in your new model. So this is the overview architecture of the QML. You have the data sets of x1, x2. You convert those states into quantum states. Then you append those quantum states into ansatz. Once you append and train those ansatz, you measure those circuit. Once you measured, and you can give it to the optimizer, that we can discuss in the next slide now. So measurement is nothing but you have to measure the qubits, each qubits. So to measure the qubit, one has to select the observables of the qubit itself. So again, this observable itself depend on problem to problem, and it also depend on circuit to circuit actually. So you have to select your observables carefully such that you will get very good efficiency. Then classical optimizers are nothing but you can go with any classical optimizers, which is gradient based or non-gradient based. There are
Through like
Yeah,
from our side, somebody
okay.
ended the meeting. Yeah.
It's okay. Cool.
Okay.
So
Continue.
let me know once my screen is visible.
Not yet.
Okay, 1 minute.
Mhm.
Yeah, I guess it's visible now.
Yeah, it's visible. Continue.
So we are at selection of this observables, I guess. So we made, yeah, we were at the optimizers. So we were discussing there are a lot of optimizers or classical available. So which can be like gradient based or non-gradient based. Again, these optimizers are completely based upon your problem. So there are such cases in classical machine learning or even in quantum machine learning. You may end up in barren plateau. There are a lot of ways in classical machine learning itself to solve the barren plateau. So again, those things are completely into a classical. It's not into quantum. So post processing is nothing but once you measure the quantum state, you have to convert. Once you measure the quantum state, you will be getting some classical values which can be again the binary values, so you can map those state into a label. So once you label that, you can check, you can calculate or you can measure your error rates, and you can mitigate those, you can optimize those error rates by optimizing the parameters and sending back those parameters to your ansatz again. And this is a kind of iterative loop. One who knows the machine learning, this is kind of the same technique. So once you have the optimized parameters, you just keep optimize it and iteratively until you are getting this best solution. So again, in quantum, the best solution means the finding the ground state of the quantum state itself. So there are the last two points, which is effect of noise channels in the QML models and error correction and error mitigation. These are the most area that one we have to consider, particularly in quantum machine learning. So when we have hardware which cannot be completely noise free or 100% efficient hardware. Currently we have noise scale noise intermediate scale quantum hardwares which are completely exposed to hardware. We are trying to become fault tolerant quantum computer. Anyway, until going to that point, we have to take care of these noise channels. So there are a lot of different noise channels that is exhibit in hardware. Popular and simplest ones are bit flip and facelift, and apart from those channels, there are amplitude damping channels and squeezed amplitude damping channels and other out-in channels, and there are different noise channels are there. We have to consider these kind of noise channels as well while we are constructing our QML, quantum neural network itself. So also we have to perform this error correction and error mitigation technique. I mean this this kind of this technique is not like it's not impossible. It is doable. So completely these error correction techniques are quite difficult to do in QML methods, since we are not having the efficient hardware as of now. Again, but we have to consider this error correction and error mitigation technique for all of our quantum neural networks. So this is the architecture of this quantum neural networks itself. So if possible, we can have another session one in coming days. We can where we can discuss more technical depth of each of these parts, like in each of the encoding systems, and we can also implement one of the sample quantum neural network for any of our data sets, and we can optimize the parameters, and we can explore into different types of neural networks that are available in Qiskit and Penillion. And also we will try to develop our own neural network, and we calculate our expressivity, entangling capability, and the circuit depth of the circuit. So from based on that feedback, we can also improvise our ansatz and make it a standard ansatz. So as we discuss this quantum neural networks, so we have to know the application of this QML itself. So the very first question is, why do we need a QML when we have very standard developed classical machine learning algorithm that can do lot of tasks, and that can be solving lot of real world problems even today? So why do we need QML? The very first question, does QML suppress classical ML? The answer is no, actually. QML cannot be in core itself. Quantum is not for every problems. Quantum computing itself for certain problems. So same goes for QML itself. QML it's not for every problems, every real world problems. QML are for only for certain problems that can be solved better in quantum when compared to classical. So as every quantum algorithm has, this QML also have the same time complexity and exploration exploration of state space, which is a huge advantage when compared to classical. And there, what are the problems that QML can solve? So there are problems like drug discovery, genomic discovery, and most importantly, there are a lot of medical image data set that has a large number of features and they are not correlated to each other. So in such cases, we can use our QML models, which can explore a lot of state bases, and it can correlate every features and integrate all those features, and it is used to better trainability score as well. So industry applications. So currently QML are in research level and emerging level. There are not that much huge industry application we have in QML than compared to classical ML. However, these QML area is developing very rapidly, and every researchers are now focusing on QML, and they are solving a lot of problems in QML. So when where we can learn this QML, I mean, there are popular programming languages called QuCODE and Penny. In their website itself, they have a lot of models and QML models that has been used. So you can start with some basic toy model that they have, and then you can, once you done some basic model, you can explore, or you can construct your own neural network, and you can start implementing those QML models. So, and one other question that may raise, can we run the QML model in hardware? So I have tried to run this QML model in hardware. As of now in Qiskit, what they have did, for each iteration, it in the quantum circuit, each iteration it is consists of one quantum circuits. So once we execute this quantum circuit in hardware, which is considered one job, so it is kind of very cost effect cost very high cost, or I would say it is kind of impossible to run this quantum neural network in hardware, since these are expensive. So maybe in future, or even very near future soon, we can run our quantum models in hardware as well. So these are the application of QML. So that's the basic thing, or overview of quantum machine learning from my end. So now the time for Q&A. If you are not able to understand any of this area of QML, please free to ask me, and we can go into that particular sites, and I can answer as many as questions possible. Again, if I am not able to answer, I will get back to you. I will research and get back to you.